Hi, I'm James, a developer at Teladoc. I'm excited to share with you how Teladoc used Elixir to build a new medication service and share some lessons we learned and tools we discovered along the way. There we go. Teladoc's transforming how patients around the world access care. The company is the world's largest and most trusted provider of virtual care services, and every day our physicians help thousands of individuals get answers to their care needs via phone, web, and our downloadable app. With a foundation in quality care, earlier this year, thanks to Elixir, we flipped the switch on new features that help further assure we're setting the bar for highest quality care and quality experience. With our new medication service, which went live a few months ago, if you opt in, it's very faded. There's supposed to be medications up there, and allow your Teladoc doctor to see your medication history. Your doctor can view your medication history, there we go, and better understand your health when treating you. If you've had a prescription filled at a pharmacy or been reimbursed by your insurance plan, our physician will likely see it. Additionally, a physician considering prescribing a specific medication can see your insurance plan, whether it covers the drug and what your copay would be. If it's not covered, your insurance plan may suggest alternatives it would pay for. Even if the drug is covered, your doctor will also see a list of any medications your insurance plan prefers to cover, which generally offer lower copays. Your doctor may even see your copay for each of those medications. Beyond saving you money, lower drug prices also improve health care because more than 20% of prescriptions nationally go unfilled, often because the patient feels they're unaffordable. Our new standalone medication service connects Teladoc with a third-party information service. Requests for patients' insurance plans and medication histories are sent to a third-party service, and responses are decoded and decorated with additional information. Requests for insurance plan-specific coverage, drug coverage, and copays for particular medications are processed locally using a database built from insurance company drug coverage data provided as flat files. I built the initial functional prototype of this new service. I was later joined by a team of colleagues, and we worked together to productionize the functional prototype. We turned on the service in February, and it's worked nearly flawlessly. It's been fast. Is it fast? I clicked. Reliable, fault-tolerant, and virtually error-free. I'll present some major lessons I've learned from this project. I believe umbrella projects are an excellent way to modularize code. After putting my first piece of business logic for determining a member's insurance plans and drug coverage eligibility inside Phoenix, I decided to break business logic out into separate applications. So I embedded Phoenix within an Elixir umbrella project. This keeps separate things separate. I didn't gen-serverize all the new applications but because each was now an individual app, I knew I could easily do so. All requests from other Teladoc apps to the new service hit endpoints in the umbrella's Phoenix sub-app. One type of request is a request for a member's insurance plan information. Phoenix routes these requests to the insurance plan service. When that request, first the insurance plan service looks in the caching database for a recent response for that member. If it doesn't find it, it creates a request, forwards it to the gateway service, which forwards it on to the third-party API. That response would get cached in the database for potential reuse, and the response would get sent back to the Phoenix sub-app. Another type of request that can be made is for a member's drug coverage for a particular drug when a physician is considering prescribing a certain medication. That gets routed to a separate drug coverage service, which will query the insurance plan service for that member's insurance plan data, which gives it pointers into the insurance database that it can use to look up that medication for that member's insurance plan. That response goes back to Phoenix, but only after it gets additional data for each of the medications, both the medication that the physician searched for and the alternative medications that the insurance plan suggests as possible alternatives. Each of those, the drug service looks into the drugs database and provides a lot of additional supplemental information. A third type of request that can come into Phoenix from other Teladoc applications is for a member's medication history. That's served by a separate sub-application. That sub-application will also look for a recently cached version of the response in the database. If it doesn't find it, it will send a specially formatted request through the gateway to the third party. That response comes back as XML. The request and response are both XML. It gets translated into Elixir data structures. It also gets translated for comprehensibility because the data comes back in a format that no human being could understand. We also supplement that information with additional data on each drug from the drugs database. For example, for deduping, the same member may have the same drug but coded differently in different medication history records. There's also a shared configuration library. We keep shared functions and shared values. And there's something called selective recursive match that I'll get to later. It's not going. No, it's going too many times. The umbrella, oh, yeah, see it went, there's a delay. Try one more time. I'm getting the, I don't know if you're seeing the spinning thing. No, you're not. Here we go. Umbrella projects have many downsides, few downsides, but Dave Thomas is going to talk about that later. I like them, but there are some issues. One is that various apps within the umbrella must all use the same version of any shared dependency. But I've been very happy overall. We've kept separate things separate, but we still get to keep everything within a single Git repo, which is convenient. And if we ever decide to extract a sub-application into a standalone application living in its own Git repo, we can easily do so. I've done this with selective recursive matches, I'll explain later. Umbrellas provide both convenience and flexibility. It's a loose confederation of almost standalone applications. So one benefit is it's a single Git repo, which is easy to work with. It can also be deployed either as a unit or as separate apps. Modularity improves readability, testability, and maintainability. We can promote a sub-application from the umbrella to its own Git repo while still using it within the umbrella. And we can scale each app independently, even dynamically. We created pools of gen servers for applications that might receive dozens or hundreds of simultaneous queries we want to run in parallel, including drug search, drug lookup, formulary logic, and XML processor. We also use connection pools for each database. Georgina McFadden gave a nice talk on Umbrella projects last year in London. She concluded by calling Umbrella projects majestic microservices, praising many of the benefits I've just praised. She also correctly noted some challenges, like Elixir tooling in areas like deployment and testing, not always working smoothly with umbrellas out of the box. Overall, though, we agree umbrellas are convenient and flexible. Structuring an Elixir project can be tricky because Elixir provides so many options. Here's how I think about this now. If the code I'm writing should run in parallel, I use a pool of gen servers that I create with Poolboy. If the code is intended to synchronize access to a resource, like a particular member's data, a gen server makes sense because it processes messages one at a time. If the code should own rights to a database or to certain database tables, it should live as a separate OTP app. We use 3 databases, and I like to keep logic associated with each database or sets of tables within a database completely separate, in line with domain-driven design. I also separated out the logic for interfacing with the third-party gateway. If the code is generic and potentially reusable, it should live in a library application. Otherwise, it can be stored in a module. Don't stub external dependencies prematurely. The third-party information service provided us with test members, test scenarios, expected outputs for those scenarios, and a test sandbox to make requests against. When other devs joined the project, one of the first questions they asked was, why aren't tests stubbing third-party dependencies? Most test suites stub third-party dependencies because external dependencies slow test execution and prevent running tests when offline or the service is unavailable. But third-party responses can change, as can any API you don't control. The longer your stubs ignore those changes, the more pain you'll experience when you notice them. Anybody who's ever used VCR knows this pain. Data in our drugs database was refreshed monthly, and the refresh often broke a few tests because a drug expired or the list of equivalent products changed slightly. These test breakages were annoying, but I valued integration tests against real-ish data. Only after I developed a feel for how drugs data or sandbox test responses changed over time did I feel comfortable tweaking test expectations to ignore insignificant changes. Over time, the test suite became less fragile, and I was confident that what we were ignoring was safe to ignore. We plan to stub many of our tests, and we built a stubbing framework that lets us return stub medication histories and drug formulary responses for all dev, QA, and UAT members, except those with valid third-party sandbox test profiles, which get forwarded to the sandbox. Used thoughtfully, mocking can be valuable. For example, I needed to test that we log an error message whenever code doesn't work as designed. The mock library let us stub functions to raise exceptions. This enabled me to test that we were logging failures correctly. First, we import the mock library. Then we specify which module we wish to mock. Here it's phoenix.eligibility. Pass-through is an option indicating that any functions not explicitly mocked should use their real implementations. We can mock multiple functions and/or function clauses, like 2 versions of find plans. After defining our mock, we can run our test in the context of the mock. Here I'm having the mock function throw an exception so I can ensure an error message gets logged. Even after we selectively ignored unimportant details and the test suite became less fragile, the full test suite still took several minutes to run. We could have brought that down to just seconds with extensive stubbing, but I valued test realism, and the greatest benefit of that came when a remote colleague joined our team and complained the tests were slow and often timing out. Because of geography, he experienced far more latency than the rest of us, so his test suite ran about 4 times slower. The correct response was not to stub tests, but to prioritize improving performance. We dramatically improved performance until that test suite ran fine thousands of miles from our office. One improvement we made was to parallelize lookups for drug details of alternative medications. We had previously been looking this up serially, and some drugs had hundreds of alternatives. Another way to improve performance is to avoid recalculating the same thing over and over. Memoization is function-level caching. If you have a pure function, meaning the same input always generates the same output, you can memoize it, remembering the output for every input you've ever processed and immediately returning the cached output value whenever you receive an input you've previously received. The memoize application is easy to use. Let's memoize this ordinary function. First, we use memoize. Then we replace def with def memo. And optionally, we can specify an expires in period if we want to consider cache responses stale after a certain amount of time has passed. Another major performance bottleneck I discovered was many unnecessary database round trips. When I initially coded drug information lookup, I implemented it as a series of sequential Ecto queries. After getting serious about performance, I figured out how to leverage Ecto associations, joins, and preloading to merge a bunch of these queries into a single, ugly but effective query, eliminating many expensive database round trips. Getting this query working required some trial and error. Elixir's explicit preloading was more painful than Rails's automated preloading. I also struggled to figure out nested preloading because the documented examples went only 1 or 2 levels deep. Despite this, I still really like that Elixir gives you the option to avoid unnecessary preloading. The query I just showed highlights the trade-offs we developers must make every day. I originally wrote my code to be modular, clear, and maintainable. But when pieces of that code proved to be highly inefficient performance bottlenecks, I sacrificed some code clarity to dramatically boost performance. I had to complect my code, reducing modularity and clarity to improve performance. A powerful weapon against complecting code into giant balls of mud is function composition, snapping functions together like Legos. Legos interoperate cleanly and can be mixed and matched because they share a standard interface. Snapping standardized building blocks together keeps code modular, clear, and dry, which is what my mouth is right now. Ecto query composition is like playing with Legos. The giant query I showed a minute ago is returned from a private method, base search, which is used by 2 public functions. One searches by product ID, the other searches by drug code and brand code. Because Ecto is composable, I was able to dry up, it keeps coming up, these 2 searches by extracting that shared giant Ecto query. You can build up your Ecto query in steps by passing it into the Ecto query.from function however many times you desire. This query handles drugs with and without brand codes and can include or exclude obsolete drugs. Query composition lets us write this as 1 function rather than 4. The first chunk of code restricts the search to just the specified drug code. The second code chunk further restricts the search to either the generic version of the drug or to drugs with the specified brand code. The third chunk conditionally excludes obsolete medications, thank you. And the exclusion code lives in a separate function, which is possible thanks to function composition. As I made the previous slide, I realized Ecto query composability allows extracting out all 4 queries into separate functions and refactoring this to an incredibly clean top-level function. You call base search and then just filter based on drug code, product, and obsolete. Networks are unreliable, so you'll want to intentionally design your application's response to network failure. If a service is down or unreachable due to network problems, your app should detect that. Stop sending more requests to the non-responsive service and respond to the requester with an immediate failure response. There's no reason to send the service another request that's likely to time out or keep the caller of your service waiting on a response likely to be a failure. Continuing to send requests to a failing service also makes it even harder for that service to recover. But you should periodically send a few requests through so you detect when the service becomes reachable and responsive again. This is called the circuit breaker pattern. We use an Erlang application called Fuse to make our medication service smoothly handle any future networking or website availability problems. When you install a Fuse, you name it and configure it through a tuple of options. The first tuple element specifies the situation under which the fuse should blow. Here we're saying we'll tolerate one failure every 1,000 milliseconds and trip the circuit breaker on the second failure. The second tuple element specifies the strategy for resetting a blown fuse. Here we're resetting it after 20 seconds. You can ask the fuse its current status. It will respond with either blown or OK. You tell the fuse about a failure by calling fuse.melt, which increments the failure count. This could blow the fuse depending on the strategy and current failure count. You can query the fuse for its current status and use its response to either do the thing or do whatever you do when the fuse is blown. Here, if everything's normal, we launch the missiles. If the fuse is blown, we report our inability to destroy the world today. Fuse.circuitDisable allows you to manually disable a circuit, effectively blowing the fuse till it's manually re-enabled. Fuse.circuitEnable toggles the feature back on. Fuse demonstrates another valuable lesson. You may not find an Elixir library that does what you want, but you may well find an Erlang library, because Erlang's been around for decades, and Jose Valim wisely made Elixir 100% compatible with Erlang code. Using Erlang code within Elixir is quite straightforward. The top code is Elixir code, the bottom code is the equivalent Erlang code, I think, which looks remarkably similar. It's a journey, and I'm still on that journey. The Elixir team recently published recommendations titled Library Guidelines that I recommend taking a few minutes to read. One guideline is to avoid spawning unsupervised child processes. As a parent of two, I can confirm this is great advice. These troublemakers aren't my kids. But sometimes you need to walk before you can run, and sometimes you're willing to get most of the results with half the effort, which is what I initially did when I had to parallelize certain operations to dramatically improve performance. Here's a quick and dirty way to parallelize operations. For each alternative drug in a list, I spun up an unsupervised asynchronous task to attach drug details. I collected up the results and filtered out any responses lacking drug details. Eyeballing production logs suggests this approach works about 99.99% of the time. Your mileage may vary. When I initially implemented this with unsupervised processes, I felt dirty. I knew I was being bad. But it's smart to take on technical debt when you're making a conscious tactical or strategic choice to move faster today at the expense of slower future development. My rule is, if the shortcut's so small that it's not worth making a JIRA card, just take the time and do it right. If it's worth making a JIRA card, incur the technical debt, create a card in the backlog. That's what I did. And we did subsequently improve this code. Rather than attempt to anticipate every way your code and hardware could possibly fail, Erlang and Elixir preach, let it fail. The let it crash philosophy is brilliant for handling idiosyncratic, sporadic failures. It's impossible to predict all the ways your code can occasionally fail, and trying to guard against them all adds tremendous complexity to your code. After going live, our service handled many thousands of requests per day, and each day we experienced a few rare events where the system sent an error response rather than the correct response. When I investigated those sporadic failures, I couldn't replicate any of them. They all succeeded when I retried them. Since these failures succeeded when I retried them, I decided to add a single retry attempt per failure. I wrapped each call using Elixir retry, letting each call get one mulligan. After the first failure, it would try the same call one more time. In production, this retry logic has, in fact, turned some initial failures into successes. Implementing this using Elixir retry was trivial. Just use retry, specify a retry delay, then wrap your function call with retry with and the delay to let your function have one mulligan. You can specify more sophisticated retry strategies like exponential backoff. Testing this was harder because it required stubbing a reliable function call to make it fail. I initially did this using the Erlang library mech, Again, don't be afraid to use Erlang libraries. Once you learn to translate the syntax, they're quite usable from within Elixir. We converted the tests to mock for Elixir compatibility. To build my functional prototype, I took data files, parsed them, stored them in a new database I created, then used that database to create the medication service and test suite. After I completed the prototype, our database team made extensive changes to bring my database into sync with their conventions, tooling, standard practices, and reporting and analytics processes. I was scared to convert from the old database to the new one because the changes were so extensive. I feared my code would break in many ways, forcing a rewrite. Luckily, I had a eureka moment, realizing I could insulate my code and tests from the database changes by using Ecto to translate the new database formats into the equivalents in the original database. If I could create an anti-corruption layer or adapter layer to translate from the new data format to my original format, my code and tests wouldn't know anything had changed. This felt like the lowest risk way to proceed because I had tests proving my code was passing all the external services certification tests. And I knew I would know my adapter's complete as soon as I got the test passing against the new database. Ecto proved up to the task. It wasn't easy, 123 commits, 113 files changed, but it was much better than throwing everything away and rewriting. This is actually a 5 megabyte hard drive in 1956. I'll show you how Ecto let me adapt the new data structures to the existing code. These Ecto features are relevant to any Elixir developer who ever works with a legacy database. Almost no Ecto had to change to support the database swap, because Ecto abstracts away most of the differences between Postgres and MySQL. The only thing that broke was anything I had coded in raw SQL, which was problematic due to syntax and other SQL implementation differences. Converting SQL to Ecto fixed that. Primary keys were renamed from ID to table name ID. To handle this, just set the source key on the primary key module attribute to the database primary key name. Almost every field name changed. To handle this, just set the source attribute on each field to the database field name. Regex check constraints on field values aren't enforced by MySQL, but silently ignored. I showed our lead DBA, and he was incredulous. Thanks, Obama. Postgres had been enforcing these constraints, so I feared bad data might creep in, but our ETL guru did a great job, so this was never an issue. Where I had lazily stored raw values from the info service, our chief data architect wisely translated codes into comprehensible values. For example, U and F became these much more comprehensible values. A and L became more comprehensible values. He made hundreds of such improvements. He also combined separate time and date strings into date times, which is more natural. Data's meaning is now much clearer, but my code was written to work with the info service's terse values that were optimized to minimize file size and transmit data faster and efficiently. Ecto now converts the values to avoid breaking the code. We'll likely tear down parts of the anti-corruption layer, allowing these changes to flow through to the code. This would also improve code clarity. But we'll do so one change at a time, ensuring we break nothing, rather than in a big bang. To translate a value in a database field to and from a different value in your Elixir data structures, you can create a custom Ecto type and use it in your Ecto schemas just as you use built-in Ecto types. Here I specify that the database table copay headers has a field named copay subtype code that will become copay subtype inside the Elixir struct. And the Ecto type copay subtype contains the logic for translating between database values and Elixir struct values. We now need to define bidirectional mappings for copay subtype. Ecto type is a behavior requiring that we implement 4 functions. The first is type, here a string. Second is dump, which specifies how we transform a value before dumping it into the database. Dump here processes only 2 values, DS and SL. Any other argument will return error. I first transform DS or SL to its full name, DS being drug specific. Then I prefix it with EDI copay to create the value we store in the database. Finally, the behavior requires returning a tuple with OK and the value to be stored. Another function required by Ecto type behavior is load, which loads a value from the database into Elixir. Trying to load anything other than the 2 valid database values returns error. We then strip the DB prefix EDI copay from the database value, and we convert the full name drug specific to an abbreviation DS, and return that in a tuple with OK. There's one more callback, cast, which is similar to dump. Rather than show that, I want to plug Jeffrey Lessel's excellent Working with Legacy Databases and Ecto talk from last year's Elixir Conf, which covers this in more detail. This also gives me the opportunity to say how lucky we are in the Elixir community to have so many wonderful conferences like EMPEX that generously post conference talks on YouTube, confreaks.tv, and elsewhere. I've learned so much thanks to these many great presenters. Three more who taught me a lot just about Ecto are Darren Wilson, Josh Branshaw, and Dennis. I don't know if it's Beatty or Beatty, but thank you all, and thanks for everybody who's given a talk on Elixir, because I've learned so much from you all. In Robert Frost's poem, Mending Wall, the neighbor famously says, "Good fences make good neighbors." My data translation wall let us adapt to radical database changes faster and with less risk by not changing our code or tests. While allowing the database and code to speak different languages was the quickest and safest way to swap out databases, there's a downside. We now have two domains, each with its own terms for similar concepts. Unifying the data and code into ubiquitous language would force them to co-evolve over time, but would eliminate the impedance between their distinct vocabularies and data conventions and the cognitive overhead that impedance creates. As the poem continues, why do they make good neighbors? Isn't it where there are cows? But here there are no cows. Before I built the wall, I'd ask to know what I was walling in or walling out, and to whom I was like to give offense. Something there is that doesn't love a wall, that wants it down. There's a cost to putting a wall between our database and our code, including the mental overhead of dealing with two reifications of similar concepts. We'll likely progressively standardize our code on the new data structures, but we bought ourselves the flexibility to tear down parts of our wall selectively and at times of our choosing. And by isolating changes to just one side of the wall, we avoided the risk of trying to make all necessary changes on the other side of the wall at the same time. I regret not learning and using type specs and running Dialyzer from day one. Type specs document each function's input and output types and enable Dialyzer to do type checking and detect code problems. We've begun retrofitting our code with type specs. At the start of this project, I was afraid spending time learning to create type specs would slow me down. With hindsight, taking time to learn and use type specs would have had a very high ROI. We would have spent less time staring at functions trying to figure out which to use and how to use them. This is true both of developers who joined the project later and even me after I had forgotten code I had written earlier. Types can be built-in Elixir types or new types you define. Types can be composed of other types, which can in turn be composed of other types, allowing a nested tree structure. Teladoc has recently made a commitment to give back to the open source community that benefits us so richly. I'm proud one of my colleagues contributed improvements to Joshua Nussbaum's XML builder. We're looking at open sourcing several things we built for this project that are potentially useful to others. Our project needed to extensively test deeply nested data structures by matching essential components while ignoring non-essential stuff like dates, timestamps, database IDs, request and response IDs. I created selective recursive match to do so and recently took a Saturday to do a full rewrite and add new functionality. It's available via Hex and in GitHub as recursive selective match. Recursive selective match lets you define an arbitrarily large nested expected data structure, like this map, and test whether an actual data structure matches it. The matches function ignores any keys or values present in the actual data structure that aren't in the expected data structure. You can specify things like anything, any map, any list, any struct, any integer. You can specify functions like isBinary or regexes. In this expected data structure, I specify matchers for a 3-element list, any value in an enumerated list of valid values, a number between 1 and 30, a string of at least 3 characters, a complex regex date-time expression. My thanks to all the wonderful people who granted me permission to use their photos and diagram designs. Another page of wonderful people. Thank you all for listening. Thanks to the conference organizers and sponsors for making today possible. My email is james@jameslavin. I'd love to hear from any of you, and I'll try to post a link to my slides on jameslavin.com or GitHub. Thank you all.